Welcome. What is specific heat capacity and how do you solve a specific heat capacity problem? Well, maybe you are a physics or even a chemistry student and you need to understand these concepts and be able to solve problems with specific heat capacity. And that's what we're going to be talking about here. So first of all, if you take a look at that animation on the right, you can think about if you had a boiling pot of water, like we have right there, and you put in a metal spoon and a wooden spoon into the boiling pot of water, let's say you waited 30 seconds or so, and you grabbed the metal spoon and the wooden spoon after waiting about 30 seconds, which would feel more warm? Well, the metal one would, and you probably knew that, and you probably have a concept that, yeah, metal is a much better conductor of heat and electricity than wood. And so as a result, it takes less energy to raise the temperature for metal than it does to raise the temperature of the wood per unit gram. And if you understand that concept, we can start thinking about, all right, well, what would be the concepts here or the factors that we need to take into account when we're thinking about this? Well, certainly the amount of heat that's being added to both spoons we need to think about, as well as the change in temperature needs to be thought about, as well as the mass. It turns out that if this metal spoon was, say, 20 times the mass of the wooden spoon, it might be harder to have that temperature raise in the same amount of time, right? So you could say that mass is a significant factor or a player in this equation. And then you have this ratio that we're talking about. It turns out that this ratio is called specific heat capacity. So what do I mean? Well, specific heat capacity, it's the amount of energy needed to raise the temperature of like a gram or a kilogram of material by 1 degree Celsius or 1 Kelvin. So that's another way to think about this. And it's different for different materials, and it's even different for different materials in different states. What do I mean? I mean, this value for water is very high, and that is not the same value as H2O in the solid form, or ice, you could say. So it's still H2O, but in different states of matter, there are different specific heat capacities, even for the same material. All right, let's take a look at an example here and think about how you would do a calculation with this. So we're going to say some of the hot water shown is used for hot chocolate, and we have a mug of water that has 350 milliliters added to it, and that is boiling water. And it turns out that 1 gram of water is equal to 1 milliliter of water. So the question is, how much energy in joules has been absorbed to bring that water from room temperature, which is a chilly 15 degrees, all the way up to 100 degrees Celsius. So I'm going to go ahead and show a conversion here. Just there's a 1-to-1 relationship with milliliters of water and grams of water. That is actually an important thing to know. And we can write down what our final temperature is. We can write down what our initial temperature is. And we can write down what the specific heat of water is. So this is what I'm using here. I've often seen it as 4.186 as well. So it kind of depends on what source or problem you're working with. Be careful with that. Sometimes this is also written as 4182, meaning 4.182 times 10 to the 3 joules per kilogram. So there can be slight variations of this, so just be careful with the problem that you're dealing with. All right, so I'm going to get this out of the way so we'll have more room for the problem. We're going to isolate for our unknown here, which is the amount of energy or heat in joules that is going to be needed to bring the water temperature from room temperature up to that 100 degrees. We can go ahead and plug in our numbers and we end up with this value right here. It's measured in joules because we're dealing with energy. So joules are our most common unit for energy purposes. And we can take that Q value and put it into the first law of thermodynamics. For instance, I'll put a link up in the upper right to that screencast as well. So that's how you would do a specific heat capacity example problem. I'm going to do a second in this series where I go through a much more complex set of lab scenarios in case you have a lab that you need to solve for the final temperature of two substances that are in contact with each other, or if you have to solve for the specific heat capacity of an unknown piece of metal as it's put into a container of water, let's say. That's another type of common lab problem that you'll see. So I'll put a link to that in the upper right so you can get an idea of how to do a more complex specific heat capacity example problem. All right, so please stick around for part 2. Take care.